Now we will go to the photoelectric effect. There is a particular experimental arrangement in which we will study the photoelectric effect. So with that diagram I will show you and I will explain what is happening there, and when you change the intensity of the light what will happen, when you change the frequency of light what will happen, and there is something called as stopping potential. When we change the stopping potential what will happen, all these things one by one, step by step we are going to study now. So this is the experimental arrangement for studying the photoelectric effect. Here we can see this S is the source of light. This source produces a light and that light is passing through this way. Here we have a quartz window. Through the quartz window it is passing and it is falling on this photosensitive plate C. And this plate C and the other plate A, this is inside an evacuated chamber. And here we have a quartz window and this light is passing through the quartz window here. When the light is passing through the quartz window and falling on the photosensitive plate C, from here, due to photoelectric effect, the electrons are emitted. These electrons will move towards the plate A. Now, here the plate A is connected through a ammeter here and we have a voltage source also here. Now you see here we have a microammeter which measures the current through the circuit, and we can vary the voltage here, that is we can make this plate A more positive or more negative with respect to this one. For that one we have a source of potential here, and here we have a commutator. This commutator helps to maintain a potential which is positive or negative with respect to C. That is we can change it to positive side or negative side using this commutator. Now the light from the source S is coming through this window here. We can vary the potential, frequency of this light by using different filters here. If you use a red filter, one frequency of light will come. If you use a green filter, so we can do it for different frequencies. We can vary the frequency. Similarly, we can change the intensity of the light. To change the intensity of the light, if you take this source away, then the amount of light reaching here will be less. So we can vary the intensity of light, we can vary the frequency of light. Similarly, this A can be, the potential at A can be varied. So for that one we will use this commutator and here this rheostat. So we can make this A positive with respect to C, or we can make it negative with respect to C, or we can vary also that one. So when the light falls on the plate, photosensitive plate here, the electrons are emitted. These electrons will go to A here and we can measure how much current is passing here. So in the beginning of the experiment, this plate A is positive charge, so that all these electrons will move toward this side. And afterwards we will make it negative also, like that step by step we will do. The first experiment is to check the effect of intensity on this one. For that one what we will do is we will change the intensity of light reaching here and how much is the current, how much is the photocurrent, that we will check. So now we will move to that experiment. This is the graph for the photoelectric current for different intensity of light. When you vary the intensity, we can see along the x-axis the intensity is there, and along y-axis we have the photoelectric current. When we change the intensity, according to the intensity, what is the current that we are checking here. So what happens, you can see in the graph, this is a straight line. So this graph is a straight line, that is the intensity of light and the photocurrent are proportional. So what is actually photocurrent? Photocurrent is actually a measure of number of electrons. So the number of photoelectrons or number of electrons is proportional to the current. Or we can say if when the intensity is increasing, the photocurrent also increasing linearly. So the number of photoelectrons emitted per second is directly proportional to the intensity of incident radiation. So that factor is very, very important. That is, the number of electrons is directly depending on the intensity of light. When the intensity is more, number of photons are more. It is in the diagram for studying the photoelectric effect. We have seen we have an option for changing the potential. So when we change the potential, we will get a graph like this. So here we can see this we have three lines here. These three lines are actually three experiments using different intensities. First we will think about one intensity only, this I1. So what we done is, the first we made the potential, collector plate potential as 0, then slowly we are increasing the potential. So we can see the electrons which are reaching to the collector plate was not 100%, few electrons were not reaching. So now when you increase the potential, what happens, the electrons which were not able to reach, so that electrons also gets attracted towards the plate. So here when it is reaching to a particular value, all the electrons are reaching, so the current is maximum. After that the current is not changing, so that is called as the saturation current. So once we are reaching to the saturation current, then afterwards if you increase the collector potential also, there is no use, because already all the electrons reached there. Now when we go to the negative side, we can see that the current is reducing, that is the electrons are getting repelled. So the electrons which is having very high energy only will reach there. Now again and again when you make it more and more negative, you can see that more and more electrons will be getting reflected from here. Now when we reach to this point, here you can see the electron with the maximum kinetic energy also is getting reflected. So this potential where the electron with the maximum kinetic energy is getting reflected, that potential is called as the stopping potential. Now you see here, for different intensities we have the same stopping potential. It means that the stopping potential is independent of the intensity. Actually the stopping potential depends on the maximum kinetic energy of the electron. That is, when the stopping potential reaches, the electron with the maximum kinetic energy also gets stopped. So the maximum kinetic energy is not depending on the intensity of the radiation. That is very, very important. Now here you see we have a saturation current. This saturation current is also different for different intensities. If intensity is very high, for that one the highest saturation current, and the saturation current varies according to the intensity, and the stopping potential is independent of the intensity. It depends on the kinetic energy of the electron. The photoelectric current becomes 0 when the stopping potential is sufficient to repel the most energetic photoelectrons with the maximum kinetic energy. So from that one we can write the maximum kinetic energy of the proton can be equated to E into V0. This E into V0 is the energy gained by the electron due to this retarding potential. So that can oppose the electron with the maximum kinetic energy. Then we can write K max is equal to E into V0. This is an important result. Now here we are going to discuss the next method. That is, here in this experiment what we are doing is we are using different frequency and we are finding the effect of frequency on the stopping potential. So here you can see, here we have 3 graphs. These 3 graphs is for same intensity. That's why the saturation current is same. By maintaining the same intensity, we are using 3 frequency here. 3 frequency means it can be 3 color. So you can see here this frequency 1, nu 1 is the smallest value. So for small value the stopping potential is small, and for the nu 2 which is the next frequency, for that one we have a higher stopping potential, and for the third value we have again higher stopping potential. Higher means it is more negative, it is towards the negative side. So here we can see the stopping potential is depending on the frequency. So if the frequency is more, we have to apply more potential. That is, if the frequency is more, the electron which is coming out, it will have more kinetic energy. To stop that one, we have to use more stopping potential here. Now the stopping potential is not depending on the intensity, that you can see here. For all this one same intensity is there, and when the frequency changes, you can see the stopping potential also is different. So this is also an important result in the experiment. Here we have another graph. Here in this graph we have the stopping potential along y-axis and frequency of incident radiation along the x-axis. So this one we are doing it for 2 different metals. This is one metal. For that metal we have a particular frequency here. This is the minimum frequency required for photoelectric effect. Okay, so you can see here for this nu 0 minimum frequency, stopping potential is not required. If stopping potential is not there also, for this one or less than this one, photoelectric effect will not take place. that frequency, the minimum frequency required for photoelectric effect is different for different metals. Metal A you have one value, metal B you have another value. So the stopping potential and this one, if you take, you can see this is different for different metals. The minimum frequency required for photoelectric emission, that is different for different metal. But you can see these two lines are parallel. So these two lines are having same slope. We will discuss about the slope later. Now if you take, instead of this stopping potential, if you take kinetic energy here axis, then also the graph will be same. But there, as we are changing the axis, the slope will be different. Okay, and when it is coming here, it will touch at this y-axis. So this point where it is touching, that point also is having some importance. So that after this one we will discuss. Now we are moving to the Einstein's photoelectric equation. As per Einstein's theory, the radiation energy is built up of discrete units, the so-called quanta of energy of radiation. And each quantum of radiant energy is having a frequency nu, will have an energy of h nu. Now you see here, we have a particular frequency h nu here. This energy of this particular radiation, that is used for two purposes. One is to overcome the work function, and remaining is given as its kinetic energy. So from that one we can write the maximum kinetic energy of the electron is given by K max is equal to h nu minus nu zero. This nu zero is the work function, and this h nu is the energy carried by the photon, and in that one the remaining energy will be the kinetic energy of the photon, emitted photon. So this equation is called as the Einstein's photoelectric equation. This equation is very, very important. From Einstein's photoelectric equation, we can see one thing which is very, very important. The photoelectric emission is possible when the frequency is more than the frequency, the corresponding energy is more than the work function. That is, if h nu is more than the work function, then only photoelectric emission is possible. And from here we already have the kinetic energy is equal to E into V naught, which is equal to h nu by nu zero. Now if you replace that one here, we can write it as V naught is equal to h by E into nu minus phi naught by E. So this is equation is like a equation for a straight line. So if we compare this one with the equation for a straight line, we can see that the slope of that one is h by E. This is what we discussed previously. So the slope of that graph, previous graph what we seen, will be h by E. Similarly, if it is this side, if it is kinetic energy, then the slope will become h. If you draw one more graph, you can check that one. For that one, if instead of stopping potential, if you take kinetic energy along the y-axis, the slope will become h. And the intercept where it is intersecting the y-axis, that is phi naught by E in this graph. And if you take for kinetic energy, you will get it as phi naught, the point where the graph is intersecting in the previous graph. So we discussed the photoelectric effect in detail. So when we explained the photoelectric effect, we were able to explain this photoelectric effect using the particle theory of light. If you consider light as a particle, we can explain all these things. And again, if you consider light as a wave, we cannot explain this one, this entire photoelectric effect. So here we are considering light as a particle. So this particle is actually, it is not just like our normal particle, it is a packet of energy. This packet of energy or quanta of energy, this is called as photon. That is, when we consider light as a particle, this particle is called as photon. So it is very easy to remember, something like photo. So it is photon. Photon is the particle when we consider light as a particle.